All right, tonight what we're going to be talking about are the colligative property calculations. So basically it's going to be talking about freezing point depression and boiling point elevation. First, you're going to need to be using for these calculations the molality. And remember, molality is defined as the moles of solute per kilogram of solvent. So that's the key on the difference between molarity and molality is it's per kilogram of solvent for molality. Okay, because molarity is per liter of total solution. So this is just talking about like in the Kool-Aid scenario, the solvent, it's just talking about the water. This is talking about the total Kool-Aid, okay? Well, remember, 1,000 grams equals 1 kilogram because a lot of times we'll give it to you in kilograms or we'll give it into grams and then you'll have to convert it into kilograms. And then the difference between molarity and molality is an italicized M, lowercase, and molarity is a capital M. So it's really important that you kind of make it definitely looking lowercase for molality compared to molarity really has to be uppercase. So example, what is the molality of a solution consisting of 5 moles of NaCl in 10 kilograms of water? So using the formula of moles of solute over kilograms of solvent, I'm going to do 5.00 moles of NaCl for every 10.0 kilograms of water. And then when you multiply that out, you get 0.500 molal solution. So that's my lowercase m. It's a little italicized, I guess. All right, freezing point depression. The magnitude, meaning how much it's depressed, of the freezing point depression is directly proportional to the molal concentration when the solute is molecular. Okay, so right now we're going to kind of learn this one. And then we're going to add on to it for ionic compounds. So molecular means that they are covalent. And remember, when they are in solution, they just give off one particle. Okay, no matter what, whether they're made up of 20 different atoms or 400, they'll only give off one particle. The formula is delta T equals Km. Okay, so this F stands for freezing point depression. The K is a constant that we have to provide you, and M is its molality. Okay, so when you look at this formula, K will always be constant, and the only thing that will change will be that molality of the solution. So here are the different KF values that I'm going to be providing you on the test. Sometimes I make them negative, sometimes you see them as positive, and you just know that it's freezing point depression, so you make it negative, just to let you guys know. The main one that we're going to be using is water, and you will once again not have to memorize any of these constant values. All right, so freezing point depression. Antifreeze protects a car from freezing. It also protects it from overheating. Calculate the freezing point depression and the new freezing point of a solution containing 100 grams of ethylene glycol, which is a molecular solution. It's a molecular compound, in 500 grams of water. So the first thing you need to do is calculate its molality. So in order to do that, you need to know the moles of your solute, which is, if we had 100 grams of the C2H6O2, you do its molar mass, you get 1.61 moles. To find, then your next step is to find the molality. We know the moles of the solute. We're going to try to divide it by the kilograms of the solvent. Notice in this problem, I gave it to you 500 grams, which means I need to convert it into kilograms. So you just move over that decimal 3 times, and you get 3.22 molal. Then to find the delta T, or the change in temperature, you're going to take that constant for freezing point of 1.86, multiply by its molality, and then you get a negative 5.99 degrees Celsius. So it depressed it 5.99 degrees Celsius. Because you're talking about water, okay, as being the thing depressed, water's freezing point is 0, so 0 minus 5.99 degrees Celsius means that you are now, it will freeze at negative 5.99 degrees Celsius total. Boiling point elevation is the exact same concepts. It's where you're going to do your delta T of boiling, but your K in this case will be a positive, so you'll be going up in your boiling point, and it's also times the molality. Okay, this is for if it's molecular, meaning a covalent compound. Now, The effective molality is dealing when you have ionic compounds. So this is where this new formula that we're going to be using throughout the whole thing will come into play. So your delta F, so your freezing point depression, is affected by the total number of particles dissolved in the water. Ionic compounds dissociate in water, meaning that you get more particles present per mole of solute than with a molecular solute. Remember, with a molecular, it only gives off one. With ionic compounds, it can give off 2, 3, 4, 5, whatever. What you do is you multiply the actual molality by the number of ions present per formula dissolved to determine the effective molality. And that is what we use to determine the freezing point depression. So let's just put this into practice, I guess. So if you had a 2.5 molal solution of NaCl, NaCl is going to give off 2 ions. So what you do is you multiply, so its effective molality is 5.0 molal. CaBr2 is also, let's say its solution molality is 2.50, but its number of ions will be 3, so its effective molality is 7.5 molal. AlNO3 with parentheses 3, once again, if these were all the 2.5 molal, it's giving off 4 ions because you get 1 from that Al and 3 from that NO3, so its effective molality would be 10. Whereas FeSO4, if we look at it, we get 2 from that guy, 3 from that guy, so its effective is 5 units, so its total one would be 12.5 molality. So this is where we're talking about it actually has a significant impact on what type of salt you use, or ionic compound, or solute that you use in a solution. So once again, just to show how it works, is if you had AlNO3, if you put in water, it's going to completely dissociate into its individual ions, which means you'd get 1 Al and then 3 NO3. So this would effectively give us 4 particles. So the modification is where you do delta T equals K times M times I. What I actually like to do is call it Kim. K-I-M. So K is the constant, I is how many ions you have, and M is its normal molality. So to do a problem, we're just going to start working on it. Determine the expected boiling point of a solution made by dissolving 25 grams of barium chloride in 0.15 kilograms of water. Okay, and then it tells us the boiling point, the constant for water. So the first thing you're going to need to do to use your delta T of boiling equals K-I-M is you're going to need to know your molality. To know molality, you're going to first have to figure out the moles of barium chloride you used. So to figure out moles of barium chloride, you know that you start off with 25 grams of barium chloride, and you need to go to moles, and to do that, use its molar mass. Which is 208.3. Multiply that out, you get 0.120 moles of barium chloride. Now I need to figure out the molality. Molality, remember, equals your moles of your solute, so 0.120 moles of BaCl2. You're going to divide it by its kilograms of solvent, so 0.150 kilograms, which was given to me by the water. And when I get that, I get 0.800 molal. Okay, so now I'm ready to put it into my delta T equals K-I-M. So my K, they gave it to us, was 0.51 degrees Celsius per molality. My I for BaCl2, if I look at BaCl2, it's going to give off 2 from the Cl, and it's going to give off 1 from that, so it's a total of 3. And then its molality, which I just calculated, was 0.800 molal. So when you multiply it out, you get 1.22 degrees Celsius. So when I ask for the new boiling point, water boils at 100 degrees, okay? Exactly, and I'm going to add 1.22 degrees. So now my water will boil at 101.22 degrees Celsius. Determine the expected freezing point of a 3 molal NaCl in water. So now this is kind of nice because once again it's going to be delta TF is K-I-M. Okay, and so for this one, they tell me my K is 1.86. Notice that I didn't give it to you negative. You're going to have to understand that it's going to be freezing point. It's going to be negative. Your I in this case is going to be 2 because you get 1 from the Na, 1 from the Cl. And then your M in this case, they give it to you so I don't have to calculate it, which is really nice. Sorry, I guess I should put units here. When you multiply that out, you end up getting 11.16 degrees Celsius. Water freezes at 0 degrees traditionally, and now I'm going to depress it another 11.16 degrees Celsius, and it's actually 0.000000. So total with sig figs, it's going to depress it by negative 11.16 degrees Celsius. Rounded to the 3 sig figs, you're talking negative 10 degrees Celsius because that's only 1 sig fig. So that's what it would be as the freezing point depression. All right, hopefully you kind of understand. What you want to know is that K, once again, is always a constant. I is how many particles it gives off when in solution, and M stands for your molality. All right, have a great evening.